Hey everyone, so we're going to continue our discussion. This time we're going to move on from angular displacement. So we left off, we talked about how an object, we could talk about an object having moved, not just whether it moved left or right or up or down, but also how much of an angle it has rotated. If something made a quarter turn, we could say, oh, it's been rotated, in our case in particular, uh, half pi radians. So is that it? Is that the only thing that we can actually refer to? I mean, if it was, then this unit would be very short. Well, obviously, there's something else to talk about. Let's say we have these two wheels. Can we compare how these two wheels are moving? Are they, I mean, they're both rotating certain angles. They're both making complete circles. So what else can we say about how one rotates different than another? Well, you might have guessed that we could talk about not just how much it rotates, but in particular, how quickly it goes through that rotation. Well, we would end up calling this angular velocity because this is very similar to how regular velocity is how quickly we change our displacement. Angular velocity is going to be how quickly we change our angular displacement. Notice how the definitions are identical, just with the term angular thrown in there. So if we just take our definition for velocity, write the word angular in front of velocity and displacement, we get the rotational definition. The symbol that we're going to use for angular velocity is going to be an omega symbol. So it kind of looks like a really scripted W, but it is an omega symbol. It's a Greek symbol. And angular velocity, as I said, is defined as the rate at which angular displacement changes. If you go back to our previous the lessons and previous notes, you should have noticed that the definition of velocity is the rate at which displacement changes. Angular velocity, very similar to regular velocity, is going to be measured in radians per second because we're talking about how quickly, how many angles, radians, we change every second. Now, before we move on, let's consider the following scenario. So we have this disk, and we want to compare the angular displacement, the linear displacement, linear distance, sorry, the time slash period, the angular speeds, and the linear speeds. So this is the rotation. So this we want to compare the red and the blue dots, and we want to go through all these. Well, if we look at the angular velocity, both dots complete one full turn in the same amount of time. So the angular displacement is going to be one full rotation, or 2 pi radians. The time is going to be the same for both. So it stands to reason that our angular velocity should be the same. It completes the same angular displacement in the same amount of time. So both the red and the blue dot have the same angular velocity. But because the red dot was further away from the center and therefore had to travel a much longer distance, it was going all around the entire edge of the circle, while the blue dot was covering a much smaller circle, we can say that the red dot had to have been traveling at a much faster speed. So these 2 points, though they have the same angular speed, they will end up having different linear speeds. This is pretty much one of the reasons why sometimes things end up flying off of a rotating surface more so from the edge rather than from the center. So here we can show it once again. It's actually very clear as it plays that this does have to travel much faster. You can almost see a blur as this moves compared to the blue. All right. So we have our definition of angular velocity being how much the angular displacement changes in a certain amount of time. So we end up with this equation as our angular velocity equation. Omega equals theta over t. So if we know how much of an angular displacement it has, and we know how long it takes for it to complete it, we can plug it into here to find the angular speed. I should point that this really only works for constant angular speeds, or I should say average angular speeds. Once again, angular speed is measured in radians per second. The one thing I do want to point out is sometimes, I don't really expect it to happen too much, but sometimes you might see the unit given in what's called RPMs. This is more of an American unit. It stands for revolutions per minute, and you're going to end up having to convert. Now, really quickly on how to convert, the best way is to use dimensional analysis. So if you want to know 1 revolution per minute, what you're going to do is I want to change the revolutions into radians, because that's our ultimate goal, is to get radians per second. So I want to multiply it by something where radians is up top and revolutions is on the bottom, so that the revolution unit cancels out, leaving me with the radians. So by definition, 1 revolution is 2 pi radians. Similarly, and then when I multiply, it's going to go 2 rev. So I'm going to end up with 2 pi radians per minute. Similarly, for the minutes, I also want to get rid of that with dimensional analysis. In the end, I want seconds to be on the bottom, so I'm going to have minutes up top to cancel it out. And through our just standard knowledge, 1 minute is equal to 60 seconds. The minutes cancel out. So when I cross through, 2 pi over 60 radians per second, or pi over 30. So this is kind of the method that I recommend doing, dimensional analysis. It's the easiest thing, though you could always figure this out through the conversion by setting up some sort of proportion, though you want to make sure that you set up the proportion properly if you're going to do it that way. All right. Now, another thing that we could do is we could actually take the equation that we had for the angular displacement, the one that looked like this, and we can get a similar conversion between linear speed and angular speed. Since theta can get us omega, or the angular velocity, just by dividing by time, if I divide the other side by time, because whatever you do to one side of the equation, you have to do to the other. Well, distance divided by time is just a speed. Theta divided by time is an omega. And I'm left with this equation, V equals omega r. Once again, this is something that's not on the reference table. This is something that you can also figure out through dimensional analysis. Velocity is in meters. Omega is radians per second. Oh, sorry, meters per second. This is radians per second, so I have to multiply it by meters in order for the units to work out. I should point out that technically radians is not an actual unit. It's not something that you really have to put in, though for the most part, I'm probably going to want to make sure that you include it just to be on the safe side. But that's one of the reasons why it just kind of disappears when you multiply it by meters, because it's really meant more as a placeholder to say that that we're doing stuff with angles, that we're doing things with rotations, and that's important. So it's only meant as a placeholder. It's not an actual unit itself. All right. So far, these are our 3 equations. Again, 2 of the equations are conversions, going from linear values to angular values, and one of them is actually an angular equation, so dealing with pretty much all angular terms. One thing to point out is that none of these equations are actually on the reference table. The ones that we're going to talk about later on, they will appear. It's not like there's no equations on the reference table, but these in particular are not on the reference table. All right. So let's practice this question. Pause the video, work itself, and we'll go over in a second. All right, so here we have a car traveling at speed. It's 23 meters per second, and we want to find the angular velocity of the car's wheels. So one thing to note about this is actually something that's going to become a lot more important in, I guess, when we start talking about energy. But if there's something that's rolling on a surface, it just so happens that the linear speed is going to match the speed of an object that's at the edge of the surface. So when we say that this car travels with a speed of 50 miles, 23 meters per second, we're also saying that anything on the edge of this circle has that same exact linear speed. So if I want to find the angular velocity, well, I have a linear speed of 23. I have a radius, which is not 80, but 40 centimeters. So this requires me to use my conversion equation, V equals omega r. Plugging my numbers in for 23 and 0.4 meters because we have to convert. And we end up getting that the angular speed is going to be 57.5 radians per second. So every second, this wheel ends up turning about 57 radians, 57.5. Now, just to clarify, what would that actually mean? Let me just get out the calculations. So 2 pi, we said, was one full rotation. So one rotation is going to be 6.3 radians. So when we say that it rotates 57.5 radians every second, what we're really saying is that it rotates almost 9 times, a little bit over 9 times every second, which is pretty fast. All right. So here's the next question. Pause the video, work yourself, and we'll go over in a second. All right. Now, for this question, the Earth's rotating, and we want to know the angular speed, both in radians per second and RPMs. Like I said, typically you're really only going to be focused on radians per second, but it's important to actually practice with RPMs because it does pop up every now and then. Maybe not in the AP, but you'll definitely see it in college and also just in general life. So let's start with the radians per second. Once again, we have to figure out which of the equations we're going to use. We're not going to use the conversion one because we don't have any of the linears. We don't have the linear speed. So instead, what we're going to do is use the angular equation, omega equals theta over t. So I had to think about, well, what is theta and what is t? Like, they didn't tell me any of this stuff, except this is information we already know. We know that in one day, it completes one full rotation. One rotation is 2 pi radians. And one day is going to be 24 hours times 60 minutes times 60 seconds. So if we do 2 pi divided by 24 times 60 times 60, we'll end up getting 7.27 times 10 to the negative fifth radians per second. So that's going to be our angular speed in radians per second. Now for part B, to find the revolutions per minute, it's going to be a little bit different. So we're going to use the same exact equation, except this time, instead of plugging in 2 pi for the theta, well, we had to match the units, revolutions per minute. The Earth makes one full revolution in 24 hours times 60 minutes. So one revolution times 24 by 60 gets me, that's the wrong unit, RPM, or revolutions per minute. So it's 6.94 times 10 to the negative 4 RPMs. If you wanted to, you could have also found a way to convert this. Like I said, you could have done this, 7.27 times 10 to the negative fifth. You could have used dimensional analysis. I want the radians to be canceled out, so I put that in the bottom. I want revolutions up top. One revolution is 2 pi radians. Seconds, I want to cancel out the seconds in the denominator, so I put seconds in the numerator and minutes up top. 1 minute is 60 seconds. So multiply through. You're essentially going to do 7.27 times 60 times 10 to the negative fifth divided by 2 pi. And you should end up getting 6.94 times 10 to the negative 4 because the radians drop out, the seconds drop out, and we're left with revolutions per minute. You could have also done some sort of proportion. So if you wanted to do a proportion, it could have looked something like this. This radians per second equals X revolutions per minute. Normally you wouldn't you don't put units on variables like an unknown X, but I'm putting it here just for reference. If you look back in what I wrote before, I mentioned that 1 RPM was pi divided by 30 radians per second. I do this so that the units cancel out. I have, like over like, like over like. So if I do this math, we end up seeing pretty much the same thing, that it's going to be 30 times 7.27 times 10 to the negative fifth divided by pi. And again, that should also get me this answer. And that's pretty it for now. There's other things that we're going to talk about, but I'll save that for the next video. So again, you want to make sure that you're keeping track of what equations are being used for conversion, what's going to be used for the calculation equations. Remember that a lot of the equations you're not given on the reference table, so you just have to know. You'll have to figure out a way to remember them as easily as possible. And that's pretty much it. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.